Thank you, and thank you very much to everybody, and thanks to the organizers for inviting me. It's always a pleasure to be back in Rio and an honor to be speaking at IMPA. In this case, I'm extra honored to be part of the celebrations for Welington's birthday. So I will be talking about Markov maps of the real line, expanding Markov maps of the real line. A picture is going to come soon, don't worry. So most people here know Markov maps of the unit interval. Just expand the concept to the real line, and that's pretty much what it is. You have some standard assumptions here. So you have a partition of R into intervals, and then on each of these intervals, your map maps this interval into a union of adjacent intervals in a twice differentiable way, and the differentiability should go up to the boundary, so you have to have an extension which is differentiable up to the boundary. You want this map to be uniformly expanding, you have it here, and you want the usual condition on distortion condition. In this case, since you are working in R, you also want an extra condition. The Lebesgue measure of this interval shouldn't be too big. This is a picture, more or less. I mean, this is what these maps look like. I should say, actually, that the talk will be divided into two parts, basically. One part will discuss the exactness of these maps, and the other part it's more, let's say, sophisticated, if you wish, or exotic topic, which is mixing for these maps. And mixing for these maps is something different than usual mixing. In the case, and which is the case that I'm interested in, they preserve an infinite measure. Then mixing is a touchy definition here. Anyway, anytime you have a Markov map, you may think of looking at the transition matrix for this Markov map, because a Markov map is pretty much akin to a random walk. And in fact, if your Markov map is piecewise linear, it is a random walk in all senses. So the elements of this matrix are the numbers p, j, k, given by the percentage of points in ij that visit ik in the next iteration of the map. So, and when you have a Markov chain, then there is this business about classification of states of a Markov chain, and you will see why it's interesting for the purposes of this talk. So you say, here we use the language of, let's say, electrical communication, so feeds and signals and things like this. So you say that the interval ij feeds ik, or the state j feeds the state k, if you send some measure from j to k at some time. I mean, if you're able to send some probability from j to k. If the reverse happens as well, then you say that j communicates with k. So now you have an equivalence relation. It's an equivalence relation if you assume the convention that ij communicates with itself. This is not an hypothesis. This is a convention. I mean, even if it doesn't happen, you just assume that it happens. I mean, so then you have equivalence classes, which are called, in the lingo here, they are called communicating classes. Okay, an essential class is a communicating class which has no outward leaks. So in this case, you have two essential classes. An isolated class is an essential class which has no outward leaks and also no inward feeds. So in this case, you also have two isolated classes. But if you add this feed there, then you have one terminal class, which is this one, and then you have this thing which is not an essential class anymore, because now you do have leaks outside. So in this case, you have a terminal class and a Bayesian of attraction for your terminal class. Okay, then since we're talking about states, but really we are interested in intervals, these states represent Markov intervals on the real line. So to each class, to each essential class, you associate a set, which is the union of this of the interval associated to the class. All right, so you call T irreducible if there is only one communicating class. And this is a non-standard definition, really. Markov indecomposable is a little weaker definition. If the set of states for your Markov map, which is bijective with Z, which you can call it Z, is connected via the relation, I mean, if a state feeds another state, or vice versa, remember for the communication relation, you had and, not or. Then you say that they are connected in some way. And then if you only have one connected component for the graph that comes out of this relation, this is really not an equivalence relation, so I should have put quotation marks here, but anyway. So then you say that your map is Markov indecomposable. Let me give you an example. In this case, you're not irreducible because you don't have just one equivalence class, as I told you before, but you are Markov indecomposable because Markov indecomposable means passing from the directed graph to the undirected graph. I mean, in this case, everything is connected through this undirected graph. So this is a Markov indecomposable situation. All right, this is also standard stuff in my classification of states for a Markov chain or a Markov process. The period of a state, or in this case, the period of an interval, is the greatest common divisor of all the return times of the interval onto itself. And by the way, when I say return times, I mean the iteration of the interval completely covers the interval because of the Markov property here. So it's a very full return time. And it's standard stuff for Markov chains. It turns out that the period is an invariant number within essential classes. And then you call the system aperiodic if the period of every state is 1. Okay, so like I told you before, I'm interested also in the cases in which infinite ergodic theory kicks in, so these maps might be non-singular or even measure preserving, but they might preserve an infinite measure. And so one of the first things that you learn when you study infinite ergodic theory is the Hopf decomposition. Since recurrence is not a given in infinite ergodic theory, then you split your system into a recurrent part, which is called conservative in the business, and a dissipative part. In this case, actually, since our system is R and there is a natural concept of infinity, then we can further split. And by the way, this composition is called Hopf decomposition. So we can further split a dissipative part into two parts. The part for which all orbits have accumulation points. So the omega limit set of any orbit is different from 0. And the dissipative part for which all trajectories in fact have some escaping, so they have no accumulation points. You call this d omega and d mo. I call this thing mo because that's how you do it in LaTeX. And it's the unit of measure of electrical conductance, and that's why tech has the symbol, and I thought about using it. It's upside down omega. Anyway, so we want to study the exact components of this map in the first part of the talk. What is an exact component in this definition? It's a positive measure set which is invariant and such that the restriction of the map to this set is exact. Okay. And so some of these things, or I should say many of these things, are known for maps of the interval into itself, and especially they are known when the number of intervals is finite, because it's easy stuff. I mean, I cannot really point to a reference, but it's, as they say, folklore. I mean, everybody knows that these things are true. But I mean, here we have problems because we have the dissipative part, and we have two types of dissipative parts, and you will see that the second one is a tougher piece of cake, actually. So this is, if you wish, a structured theorem in the way of, I mean, if you're familiar with the hyperbolic theory, in the way of Piacin's theorem or Katok-Streltsyn theorem. Anyway, it says that your conservative part can be split into a number, a most countable number of components, and each component is itself made of cyclic components, as you see. I mean, it splits into d parts, and these parts are cyclic in this sense, okay? And the d power of the map on each part is exact, okay? What those structure theorem in general don't tell you, which is true in this case, is that they have a lot to do, of course, with the essential classes that we were talking about. And especially, they have a lot to do with isolated classes. So each each exact component, well, not exact component, I mean, each component C alpha is actually related to an essential class in this way. This is the set associated to the class that I was telling you before. And also the vice versa works most of the time. Let's look at the first point here. So if you have a finite isolated class, then the corresponding set is, in a sense, of course, you should say, is an ergodic component with the above properties, which splits into d alpha cyclic components. And by the way, this d alpha is the period of the essential class. But then you have this other phenomenon which occurs because you have an infinity, if you wish, or because your Markov chain has infinitely many states. You can have an isolated class that is infinite. Well, it could do the same thing as before, or it could be a T-invariant subset of d mo, which is the part of the it's the dissipative part which, for which the orbits go to infinity. So this happens because, you have easy examples. If you take a simple asymmetric random walk, okay, which is skewed, basically the probability of going, I don't know, to the right is bigger than the probability of going to the left. Of course, this is an isolated class, but you cannot expect this thing to be recurrent once you represent it as a Markov map on the real line. So you have these problems as well. In theory, you would like to establish this one-to-one correspondence between isolated classes and parts of the conservative part of the map, but no, you always have exceptions because, the third element of the Hopf decomposition, the non-accumulating dissipative part, can contain a lot of things, in fact, and this is going to be our problem. Okay, so we then have a similar theorem for the first dissipative part, so the dissipative part with accumulation points. Then in this case, you may have, you consider these sets M alpha as before, but you consider them together with the whole basin of attraction, together with all their counter images. So this is the set as well. And these are associated, in general, they are associated to terminal classes of period d alpha in such a way that for every point in this component of the dissipative part, the omega limit set is your M alpha, which is the part which is associated to an essential class, okay? And on M alpha, the map is conservative ergodic, and it splits into d alpha exact components, which are cyclic. But of course, you also have a basin of attraction. And, okay, once again, you have a vice versa. If you have a finite terminal class, so an essential class which has a basin of attraction, then this corresponds to an ergodic component within the dissipative, within the omega, within the first dissipative part with the above properties. But once again, actually, if you have an infinite terminal class, you can be in the same situation as above, as here, or for the same reasons as before here, you can also be, this can also be associated to a part, to a T-invariant set within D mo, within the, let's say, more complicated dissipative part, okay? So basically, this d omega, is made of ergodic components which would like to be exact. They are exact, in fact, actually, but would like to have the same property as before, except that they have a basin of attraction. So the problem here, you're not belonging to the conservative part, so you're not recurrent. The problem is in the past, because there are non-essential states, so states which send measure to other parts of the phase space without ever receiving back measure, that, anyway, for which conservativity cannot hold, the recurrence cannot hold. Points in there will go to the omega limit set, they're going to stay there in a sense. So I don't like to call this a attractor because it's not really an attractor, but think of that. So here you're dissipative because of your past, because you have inessential states in your past, because there are points that come to the interesting parts of the phase space without ever going back. By the way, I should mention this, that if by any chance your map preserves a measure which is absolutely continuous with respect to the Lebesgue measure and vice versa, so which is equivalent to the Lebesgue measure, then the first dissipative part, the accumulating dissipative part, doesn't exist. Okay, and since every math talk should have a proof, here's the proof. It's very easy because basically somebody else has done the work for me here. You can characterize, in the case of an infinite invariant measure, you can characterize the conservative part as the set of points. You have a positive L1 function, the set of points for which this Birkhoff sum goes to infinity. That's an easy proposition which you can find in the book by Aronson. And then in our case, of course, if you have accumulation points, of course, and if you can take the function to be continuous as well, then every point actually will be in this set. So every point in d omega will be in the conservative part, which is a contradiction. I mean, unless, you can only talk about a zero measure set of points that have this property. So anyway, so then the interesting part happens on the non-accumulating dissipative part. And for that, you also have to describe a little bit what happens to the states. So as I told you before, you call inessential those states that do not belong to an essential class or in the basis of attraction of an essential class. So these are inessential states, and it happens that the union of all the inessential states, or if you wish, of all the intervals associated to inessential states, belongs in this demo, in this third part of the Hopf decomposition. Okay, and what you would like to do, you would like to characterize the exact components of this demo. And this could be very difficult. There are lots of counterexamples that you can think of in which you have a number of good properties, of good hypotheses, and still the exact components are very hard to characterize. There are counterexamples in which, in certain parts, the tail sigma algebra, so by the way, I didn't mention this, assuming that everybody knew, but exactness means that the tail sigma algebra of your system is trivial. So there are cases in which you have a number of good properties, but still the tail sigma algebra in some parts, so the intersection of the sigma algebra with the region of your phase space is as big and as structured as the Borel sigma algebra. So it's really very far from being exact. So, but if you add some extra assumptions, in fact, some of them are mild, some of them maybe are not so mild, you can actually describe the exact components on this part as well. And these are the assumptions. I should mention here that whatever is in green in my talk is usually not so important. You can skip it at first reading. I give conditions here, and the green part says, well, these conditions are given just on the d omega part. You don't need to give these conditions. So if you know that some part of your space is conservative because somebody told you beforehand, you don't need to verify those properties here. But in the dissipative part, if you have bounded dynamics, so there is a bounded distance between x and its iteration, and then if you have a condition on the measure of these intervals from below, remember that the first condition, which I called A1, was that the measure of these intervals was bounded above, and now I want it bounded below, at least on this dissipative part. And especially, this is the not so mild condition. If you require that every interval in this part has an image which covers it, so by the way, this gives you automatically that the map is aperiodic, because you have at least one return time equal to 1. So the greatest common divisor of all the return times for all the intervals is 1. But if you have these conditions, you can actually say something. And here's the theorem. Under some of these conditions, you can split the omega into two parts, the sets, the points that go to infinity, the points that go to minus infinity. Under A6 as well, these two parts have either zero measure or an infinite measure. And especially under A7, they are exact or null. Okay, so this is, with this hypothesis, you also have a complete characterization of the exact components for this part as well. Okay, so for the purposes of the second part of the talk, I want to focus on some examples. The first example, that may be the easiest example, is so-called Quasi Lift. So you basically, you decide on a branch of your map, and then you duplicate it all over the place in a way that the map becomes translation invariant. And let's say that the size of this interval is A for all of them. So yes, this is a translation invariant map. In the business of infinite ergodic theory, people like to call this thing Z extensions, but this has certain properties. I mean, these branches are done in a certain way. They have this property here, which I was requiring in the assumption A7 before, so I want this map to have this property. So these are special type of Z extension, as they call them. So I basically invented another name for that. I mean, this is not a lift, a topological lift, because these parts are disconnected, but this is a quasi lift. And you have to think of, actually, don't think of it, because it will be a property that a quasi lift of an expanding circle map, in fact, preserves a measure which is equivalent to the Lebesgue measure, verifies A5 and A6 with the hypothesis before, and is exact. It's pretty easy to find out. In fact, I mean, this map is an extension, or if you wish, it factors down to a uniformly expanding Markov map of the circle, and then all the properties basically gets lifted up to this map. If you wish, this is the natural extension. I mean, it's the universal extension of a map which is uniformly expanding on a circle. So the next model that one might want to look at is just a small complication on this type of maps. So you can think of finite modifications of quasi-lift. So you take a quasi-lift and you modify it in a compact region of your phase space. Okay? You also want to ask that this map keeps verifying A1 and A7. It's easy to actually make a compact modification that destroys this thing. So you want to ask that these properties hold. Okay? And then, once again, in terms of the exactness properties for these maps, if you have one such map which verifies this hypothesis, already asked that, is Markov indecomposable. By the way, I mentioned this before. Let me mention it again. Markov indecomposable also means that if you have an invariant set which is Markov measurable, which is the union of Markov intervals, then this invariant set has to be the whole R, the whole phase space. And this is what you use to actually prove this. You also want this map to preserve a measure which is absolutely continuous with respect to M. And if you don't have this hypothesis, once again, all sorts of counterexamples come up, and you can destroy exactness very easily. Well, then the map is exact. By the way, I mean, in the previous slide, I mean, this picture, it's easy to create a finite modification of quasi-lift, which preserves the same measure of the quasi-lift. I mean, this is one example. I mean, as long as you make the modification so that horizontally you have the same balance of slopes here of the derivative as in the original map, then, of course, I mean, if you think of the transfer operator applied to these kinds of maps, of course, this new map is going to be different, but it's going to preserve the same measure. So, I mean, the easiest modification that you can do is make a modification that preserves the same measure as the original map. All right, so here comes the second part. I was interested in these two examples and in the exact properties because exactness gives me a tool to prove some definitions of mixing that I proposed a few years ago and that I like. That's the reason why I proposed them, which are called infinite mixing, or if you wish, infinite volume mixing. And they go as follows. So this is general stuff. Now for like the next 2 or 3 slides, forget about R. This is a general phase space which preserves a sigma finite infinite measure. Okay. And then you want to look at bigger and bigger parts of this phase space. This is a concept that if you come from physics or if you studied a little bit of statistical mechanics will be very familiar to you. I mean, when you have to describe an infinite set, you want to describe it on larger and larger boxes. and see what happens. I mean, because you want probability measures and you don't have probability measures, so you restrict your system to a large box, you normalize everything to the large box. If something happens and this something stays good to the limit, then you have certain properties. So this is pretty much the idea. So on your system, you define on a case-by-case basis, depending on what system you have and what you can prove or want to prove for this system, you define a family of large boxes, which you call the exhaustive family, as in exhausting the whole phase space. So each of these large boxes is a finite measure set, and for coherence, you want to have at least one increasing subsequence that covers the whole space. But in general, like in our case, in fact, you want more. I mean, you would like to have a much richer exhaustive family, not just one increasing sequence, but a bunch of increasing sequences which can be located all over the place. Okay? So once again, I mentioned this, you choose this on a case-by-case basis. I'm not giving you a theory that tells you how to define these large boxes in every case. I mean, it depends on what you can prove and also depends on what you want to prove. So then once you have these large boxes, you go to infinite volume limit, or as they say in statistical mechanics, thermodynamic limit. So in my case, I want some uniformity. So when I write this, so the large box going to the whole of phase space, I mean I want a uniform limit in which the large box gets larger no matter where it is. I only look at its measure, and then whatever happens or whatever limit I have is uniform in the position of the box or in the shape of the box, and only depends on the measure. Okay. Also, for this to make sense, both mathematically and, if you wish, physically, you want a large box to be, I mean, studying a dynamical system makes sense, or most of the time, at least in ergodic theory, makes sense when your phase space is invariant for the map. I mean, you keep iterating, you keep having the same phase space, no contractions or expansions, or you don't exceed your phase space. But when you have a large box, of course, this is not invariant for the dynamics, so, and you cannot expect it to be. But if it is almost invariant, so if you have that the difference between, I mean, if you apply your map for a finite amount of time on a large box, and the difference, the symmetric difference between this and that is of the order, of a lower order than the measure of the box. So usually in physics, this is the order of the boundary of the box. So you have, this is the typical picture that you will see in a statistical mechanics class. And you have a large box, and then there are iterations of things in here with points, or if you talk about dynamics, or if you talk about spins or anything like this, they iterate with something which is outside. So, and then if this iteration is limited to something which is of the order of the boundary of the box, and if the box is chosen in non-pathological way, so that the boundary of the box is of lower order than the measure of the box, then things are good. I mean, of course, in the limit, they're going to be washed out. This is the typical setup. Okay, so we want that both for physical reasons and also for mathematical reasons, because, did I skip something? No. Okay. That's the next slide. So let's go back to our maps. If you have translation in different maps, translation in different means simply that you have a map and you translate it, and of course it's a different map. It doesn't look too different. It's a map of the same nature. For instance, a map that preserves a finite measure is not translation indifferent for me, because I mean, somehow it prefers a certain region of the phase space. Okay? A quasi lift is, of course, translation indifferent. Also, a finite modification of quasi lift is translation indifference, because if you make your modification or perturbation here above the origin or right there, I mean, it's not like a big of a deal. The properties of the map, the expansivity, the distortion constant, stay uniform throughout R, and then for me, this is what I call translation indifferent. It's not a formal definition. So if you have a translation indifferent map, it only makes sense that your large boxes are also translation indifferent. I mean, you don't have just one sequence of large boxes, let's say, originating at the origin. You can take large boxes all over the place. I mean, things should be uniform in the position of your large box. So this is our choice for these types of maps. And so now the infinite volume limit, this limit here, corresponds to taking the size of the box, sending it to infinity uniformly in the position of the box. This is what it means in this particular case. So you only look at your map over intervals, over large intervals. Okay, why do you do this? Because what do you observe? I mean, choosing V is choosing where to observe things. Now, we want to also choose what to observe on large boxes. And here come the global observables, so, which is actually somehow the novelty of this type of notion of mixing, which I'm going to introduce in a second. A global observable is basically the opposite of an L1 function. An L1 function you can think of is a very close relative to a compactly supported function. So it's a function that looks at a finite portion of the phase space. A global observable is, think of the furthest example of a function. So it's something that is more or less supported. I mean, it looks pretty much the same all over the phase space. Once again, this is supposed to be translation indifferent, if not translation invariant. So this is a general idea. Once again, I'm not telling you what the global observables are for each system that you can think of. You have to choose your own global observable depending on what you like and what you can prove. But I'm giving you general ideas. So it should be a subset of L infinity. You want bounded observables because soon enough we'll couple them with L1 functions. So it's a good coupling, L1 versus L infinity. But of course, you don't take the whole of L infinity. You take a subclass of L infinity. And it could be a very, very narrow subclass. But it should at least have this property. So let me say it's an axiomatic property. It should have an infinite volume average. Remember, I defined the infinite volume limit. So if you take your function, you average it over a large box, once again, independent of the position of the box, only depending on the measure of the box, then uniformly this goes to a limit which is a number. And so this, as I call it, infinite volume average plays the role of the measure of an observable. L1 observable have the measure mu. Global observables have the quote-unquote measure. Of course, this is not a measure. It's a finite, as finiteness, the finite property, the finite additivity property, but certainly it's not sigma anything. So it's a positive linear functional, let's say. At least that is true. So with this definition and with the business about the large box being not, having only surface effects, if you wish, so which was one of the assumptions, you can actually prove that this functional is dynamics invariant, which is what you want to have. And so if you're interested in mixing, by the way, once again, a reminder that these definitions depend on your choice of V or the exhaustive family and on your choice of global observables. So once you have global observables and you have this functional, what could be a good definition of mixing? Mixing means basically decay of correlation, means that two observables correlate. You take one observable and the evolution of another observable, they decorrelate. Now, how do you translate the correlation? Now that you have global observables and this thing which stands for the measure, this could be a good definition. Of course, this definition has mathematical problems because global observables have the axiomatic property to possess an infinite volume average. So these two numbers are well defined, and also the infinite volume average of the evolution of the evolution of f is well defined. But there's no reason why the product of these two should have an infinite volume average. So the left-hand side here might not exist. So you may take a position and say, well, who cares? If when this is not verified, I don't look at it at all. So you only look at observable for which it exists. Or you may define, if the left-hand side does not exist, then I declare that the system is not mixing. Or you can improve your mathematical situation by looking at another definition. By the way, I call this GGM1. G stands for global mixing. And then this global mixing too. You have a somewhat stronger definition. So this has no mathematical problem, no well-posedness problem, let's say. It has mathematical problems, meaning you have to prove it in many cases. But so if you take a limit in which both the time and the size of the box go to infinity in independent ways, I'm going to tell you in a second what this notation means, and they, the limit is what it has to be, then you say that the system is GGM2 mixing. So what does that mean? It means that. It means if both the time and the size of the box are large independently of each other, then the left-hand side is as close as you want to the purported limit. Okay. So, but global mixing is not the whole story, it's not the whole business, because, well, if you have a system which has, for instance, an invariant set, which is finite measure, global mixing doesn't even see it. I mean, anything which is finite measure is absolutely under the radar for these definitions. So you want to consider cases like this. You might not want to call it mixing, or you might want to do something else. And also, more importantly, for my point of view on this business, is that local mixing doesn't really see, is not very well suited to study the statistical properties of dynamical systems. By that, people in my business usually mean, actually, which is the same business as yours, but they like to say this a lot in conferences in ergodic theory. It means that you have you have an initial measure, so you take your initial condition according to a probability measure, and instead of evolving the point, you wish to evolve the initial measure with respect to the transfer operator, and you want to see if this initial measure, so if this evolution of, if you wish, the push forward of the initial measure converges to something, so it goes to an equilibrium measure in some sense. And of course, if in our cases, think of a random walk, you cannot expect to put an initial, a probability measure, and since there is infinite room and this spreads all over the place, then you cannot expect this to converge to anything. In fact, the density of your measure is going to be spread out more and more, thinner and thinner intensity, and so it will not converge to anything, or if you wish, it converge to zero locally. So you have to define a way to say that an initial measure converges to something. So anyway, for this, you need another player, which are the local observable, and local observables are subspaces. Once again, it's up to you to choose your local observables. In general, you actually choose the whole of L1. They are subspaces of L1. Just think of densities, basically. So once you have global and local observable, one good way, especially to implement what I just told you, to define a mixing which looks at the coupling between a global and a local observable, that's why this is called GLM, so global local mixing. One good way is this. So you evolve your global observable, then you multiply it by your local observable. So this thing is now an L1 function, the product of this. So you can measure with the measure mu. And if this splits asymptotically, if this factorizes into the product of G measured by mu and F measured by mu bar, then you can say that this system is mixing in some sense. I'll tell you later why I call it 2 and not 1. And so, what's the time? Okay. So in the interpretation I was saying before, sorry. Okay. You can think of this as, instead of evolving the observable, you define mu g as the measure mu against the density g when g is a density. So you take g to be positive with integral 1, so it's an actual density. So the same definition before, you see, translate into that. Instead of thinking of evolving g, you look at the dual thing, so you evolve the measure. And so the evolution of the measure converges to this functional, which I call infinite volume average, with f, the global observables, playing the role of test functions. So you have a very, very weak form of convergence to equilibrium, which you couldn't have for infinite volume, for dynamical system preserving an infinite measure. So, well, you have a bunch of other definitions. You can do the same with local observables which have zero average, and these two definitions are not equivalent. They are equivalent in finite ergodic theory because you can always add a constant to these guys here, but you cannot add a constant to a local observable and let it stay local, then it will become a global observable. So these two definitions, in fact, one is stronger than the other. They're This is easy to verify in many cases. This is hard to verify in many cases. What does it mean? It means that if you have two initial densities and you evolve them in the way that I told you before, you're not guaranteed that any of them goes to any limit, but you're guaranteed that the difference goes to 0. Okay, so it's a weaker form of looking at the statistical properties of asymptotic statistical properties of dynamical system. And then you have a uniform version of the same thing, which I will not talk about. It's not so important. How much time do I have? Okay, so as you could see from the previous slides, I mean, there is a hierarchy of definitions for global local mixing. This is a uniform version of that. This is a weak form of that. So you have this chain of inequalities. And also, for global mixing, one is morally stronger than the other. Morally because in order to apply GGM1, you need to know that the infinite volume average of the product exists. But if it does exist, then this is stronger than the other, which is kind of obvious because this was uniform in the size of the box and in time. And so this had only one limit in it. So of course, this is stronger. Why did I spend half of my talk talking about exactness or 3/4 of my paper proving certain things about exactness? Because if you have exactness for it's a general result. If you have exactness, then GLM1 comes for free. It's an old theorem by Lin, 1971. And GLM2 has a very easy criterion for which, I mean, it's easier to prove than in most other cases. And you have analogous results for K-mixing. But here we're talking about non-invertible maps, so let's not talk about K-mixing. So what are the choices that we take for our case? So the local observables are all integrable functions. The exhaustive family is given by what I told you before, so all intervals placed anywhere. The global observables, well, then you have to be more careful because the global observables are the real hard ones to treat. So I really want to go fast here. I mean, consider Quasi Lift for a second. So what is the simplest global observable that you can think of for a Quasi Lift? This is a Z-invariant map. It's a Z-invariant observable. In this case, everything is easy because both the dynamics and the observable can factor down to the circle, from R to the circle. And so you can use everything you know from expanding maps of the circle to prove everything you want to know. So, of course, this would be, if you only looked at periodic observables, this would be a pretty silly class. But you can do a little bit more. You can take any observable which, if averaged over Z, so this is AKF, if is the Z average, sigma is the translation by, it's the Z translation if you wish, it's the action of Z over R. So an observable whose Z average converges uniformly to a periodic observable, that will work. So for instance, quasi-periodic observables, and I'll give you one example in the next slide. Other type of random observables which do not oscillate differently in different regions of the phase space, they will all fall in this category, which I call G1. Okay, G2 instead is the class of quasi-periodic observables. Okay, for instance, okay, this is an observable which is not quasi-periodic and works for the class G1. So you have these levels plus and minus 1, but they don't need to be periodic. I mean, if you take a Z average of this thing, this goes uniformly to 0, which is, of course, 0 is a periodic observable. So observables like this, you have two classes because some results can be proved for the wider class, and some results can only be proved for the narrower class. So I'm close to the end. So for Quasi-Lift, so for translation invariant maps, you can prove GLM1 for any class of global observables, and for the biggest possible class of local observables, you can prove GLM2, which is the hard one in a sense, with respect to this class G1 that I told you just now, and with respect to the local observables L1. And you can prove this global mixing both forms with respect to the narrower class of global observables. Of course, results are weaker for finite modifications of quasi lifts. You need to require your finite modification to preserve a measure which is equivalent to the Lebesgue measure. Also, you want the infinite volume average with respect to the measure mu to be the same as the infinite volume measure with respect to the measure mu0, which was the measure that comes with the quasi-lift T0, of which T is a finite modification. So you want to have the same thing. This can be removed, but for the sake of simplicity, let me just state it like that. Well, then in this situation, you can actually prove the weaker form of global-local mixing and the weaker form of global-global mixing. There are extensions for, people in infinite ergodic theory like non-uniformly expanding maps with indifferent fixed points. We are preparing with Claudio Bonanno and Paolo Giulietti some results about global and global-local mixing for these types of maps. Here I see them in R+. You just conjugate them to an R+ map. For instance, this is the Faraday map. Okay? So we can prove certain things, which this will come out sometime soon, hopefully. And thank you very much. And happy birthday, Welington.